Questions before we get started? We got a few minutes.
Yeah, I like it.
Everybody's all on board. We have got a homework due Monday, and then we have a test on Wednesday in class on the complex variables. So there's a practice test on campus under Chapter M, and so that'll give you a good idea about how to study the test. No question.
I guess. Apparently, complex numbers. We're going to be covering complex numbers in my advanced mechanics course. I was just curious, like, is it like used heavily in advanced mechanics? Complex numbers.
Complex numbers are used throughout every subject. Anything beyond the introductory level.
Okay. All right.
E&M, quantum mechanics, ordinary mechanics, or advanced mechanics. Yeah, complex variables are used throughout.
And why is that?
I think the generic reason is because in mechanics that we have, as I mentioned, we have two initial conditions that we can specify for motion. We can start off, we can determine the initial position and the initial impetus. Those we can determine independently. As I gave an example, I have an object here and I can determine where I'm going to start, where I'm going to let go of it, and also I can determine how much impetus I give out, up or down or sideways. And those are both independent. Complex use of complex numbers allows us to capture both of those things together. Two independent factors. Complex variables allow us to do. That's kind of the general reason. It's compact. It's not necessary. You can do all of these subjects without complex variables. It's just a very compact way of encapsulating both of these independent solutions in one form. So it's not necessary at all. You can do all of it, just real numbers. Now it comes down to the Euler relation. E to the theta is cos theta plus I sine theta. So the real part is the cosine. So for a wave, there's two independent parts of the wave motion, cosine-like and sine-like. Those are both captured in the Euler relation in the complex number. Very compact way of writing those things all at one time. You have both of them present in the complex variable.
And you said it allows us to capture both the initial conditions of impetus and of its initial position.
Yeah, I'll show you how that works here.
Yes, sir. Yeah,
Because that's related to your question.
Yes, sir.
Okay, so I want to talk briefly here about going back to this general problem. There was a simple harmonic oscillator using complex variables. To solve this, I want to just give you a bigger picture here of what's going on, and also what I'm going to say here is going to apply equally to the damped harmonic oscillator and other differential equations. So remember, we have a situation where we have a differential equation like this, and we have two initial conditions, for example, and these are independent of each other. The initial position and initial velocity. And that corresponds to what you know from your experience, that I could start something off. I specify the initial height and also the initial impetus, whether it's up or down or sideways or something. So these can be set independently. So it's got to be reflected in the mathematics in that way. Okay, so we started off by trying to look for a solution to this differential equation of a particular form. This is a guess, right? Okay, and we substitute that in and we find this. Okay, and we conclude then that B must satisfy this quadratic equation. And so we find that B is complex. Well, that raises a question. If B is complex, how do we create a solution out of this, because if B is complex, then this is a complex function, but X should be real. It's kind of puzzling. Okay, so this is how it works. There are two different values of B. We rely on what's called the superposition principle. So the superposition principle in this sort of differential equation would say that if I have one solution and another solution, that the sum of the two is also a solution. So I have two different solutions here, and in principle, I have two different coefficients in front. So I have two different values of B. Call them B1 and B2. And these both solve this algebraic equation. This, what's in parentheses will vanish. So that means I have two solutions. And so the general solution can be written as a sum. Okay, so this relies on the superposition principle, which is to say that if this one is a solution by itself, and this one is a solution by itself, and the sum is also a solution. Let's check that out. We're going to substitute this whole thing into here, right? We verified each one independently satisfies the differential equation. Now let's go and put this into here. So we need the second derivative. Okay, and so now if I substitute these two into this equation, I get two terms. I get mb1 squared plus k times a1 e to the b1 plus mb2 squared plus k b2 e to the b2 t. And we said that these are independently solutions. This is 0, right? This is one of the roots here. So this vanishes, and so does this one. They both satisfy the equation independently. So now we superimpose them, that sum will also be a solution, just to the differential equation. We're not considering the problem of matching to initial conditions yet. It's coming. Okay, so that's the superposition principle, that if I have in general, if I have f of t is a solution and g of t is a solution, then the sum will be a solution. And that's because this is part of a general class of equations called linear equations, which is coming from this. I add them together. Or I could also just, if f of t is a solution, then 2f of t is a solution. 3f of t is a solution. So I can multiply any solution by a number, also come up with a solution. Okay, so far I haven't said anything about A1 and A2. Okay, and I still haven't resolved this problem about creating a real function here. Okay, so we have these two different solutions, and we demonstrated that the sum is a solution. So let's write it this way. So one is e to the I omega t. Call it a plus, a minus. And I still need to make this a solution. It needs to be real. I'm going to match the initial conditions, which are both real here. Initial position, initial velocity. Okay, so that says something. Now I can say something about these capital A's. Okay, you can see that this function is the complex conjugate of this function. To get a real number from a complex number, I can add it to its complex conjugate. That gives me a real number, right? For any complex number, this is real. It has no imaginary part. Complex number. Is that clear? How that works?
So a sub minus and a sub plus, that's just signifying that that's the positive. That's the constant, the positive
right
part.
Right.
And
this demonstration here does not depend on anything about A1 and A2. They have not yet been determined. So I have a general solution of this form, and the only restraint that has been put on it are the values of D1. The values of A have not yet been determined.
Is that, what's that say? Is that IM? Let's say
Imaginary.
Right.
Okay, so that would mean then that I could get a real number out of this for all values of T if A minus and A plus are complex conjugates of each other. See that? Because then I would have, would be the complex conjugate of that, add them together, I get a real number. And now I've gotten through this problem of having to have a real solution, right? So in other words, this is real, imaginary of x 0 for all t, if A minus is equal to A plus complex conjugate. So here's a complex number. And so I just have a complex, this is a complex number plus that gives me a real number. Okay, now I can go and match to the initial conditions and everything's going to work out fine, even though I go through this strange stuff of having complex functions. I'm going to come up in the end with a real solution. Kind of weird that I would do it this way. Okay, and everything that I'm saying also applies to other differential equations. For example, the damped harmonic oscillator, this is still true. The roots are themselves, the B's are complex, not just imaginary, but have real parts. Everything falls through. I mean, it's all the same, right? These B1 and B2 would be complex conjugates of each other. They have real parts, but they're opposite imaginary parts for the damped harmonic oscillator. Okay, so now we can match without worry. We can set x as 0. And now I'm going to set time to 0 since A plus plus A minus. Okay, and remember, A minus is the complex conjugate of A. A plus and A minus are complex. But their sum is going to be real. That's going to be the initial x. Now we need to take the derivative because we're going to match to the initial velocity. Okay, that's the velocity as a function of time. And again, it's going to be real, right? Because this thing is going to be the complex conjugate of this. Remember, when you take the complex conjugate, everywhere there's a imaginary part flip the value negative. So e to the minus I omega t becomes 2 to the I omega t. A minus becomes A plus. They're complex conjugates of each other. And minus I omega becomes plus I omega. So these are still complex conjugates added together. Right? That negative sign here, let's do it this way. Plus a negative I omega. So it makes it clear you're adding a complex number and its conjugate. So this is also real for all time. Even though I've got these complex numbers flying all over the place, they're adding up to give me always a real answer when I'm done. Okay, so let's evaluate this at time 0. And these exponentials evaluate to 1 again. So I have I omega A plus minus A minus is the initial velocity. Okay, now we're going to solve for A plus and A minus. We have two equations, 2 unknowns. And it will turn out the solution of A plus and A minus are complex conjugates of each other. But we don't need to impose that. We can just find it's the case. Let's divide by I omega here. So we get A plus minus A minus is equal to minus I b naught over omega. And now I just rewrote the second equation to make it easier to combine with the first. So I can add these 2 equations together to get A plus, and I can take the difference to get A minus. So A plus is what I get when I add these 2 together. And then I got to divide by 2 because I have 2 A pluses. So it's 1/2 x naught minus I b naught over omega. And A minus will be the complex conjugate. A minus is what you get when you subtract this one from this one. And A minus is this. And I had predicted that in order to make this thing work, it has to be complex with A plus, and that's because X has to be real forever, all time. Okay, does that help with, I went through it kind of quick, and so it maybe had left some uncertainty about how all this works. It's very interesting how you can set it all up in terms of these complex functions. But if you do it correctly, everything will be real at the end when it needs to be. Although all of the intermediate work will involve these complex functions and complex constants. That's point one. And more generally, the superposition is what we're relying on here. We have two solutions here, which are independently, each one is a solution to the differential equation. Doesn't match the initial condition, but each one solves the differential equation. So we can construct another solution to the differential equation, which is a sum of the two. And then we match these conditions, these coefficients, to match the initial conditions. That help?
Definitely.
Okay. And the same thing happens. This is generally true. If I had a damped harmonic oscillator, everything I said pretty much follows through. I just have different roots here, but everything else remains the same. Generally, right? Okay. Good. Can I erase this? So you will find the convenience of complex variables to be, I mean, it is very convenient. Everybody, I mean, that's why it's used so much. It's very compact notation, and I think generally it's true because we have in general these kind of two different independent solutions that are going through. And you'll see how this, so we saw that for the simple harmonic oscillator. You're going to see it for the wave equation coming up next, right now. We also have two different solutions for the wave, two different independent kinds of behavior for the wave equation. And again, complex variables are a nice way of putting it all together. Same thing, remember we said there was an analogy between a damped harmonic oscillator and an electrical circuit I could make out of an inductor, a capacitor, and a resistor. And so the same sort of thing happens there. I have two different things I can start this circuit off with. I can put charge on the capacitor, and I can determine how much current is flowing through the circuit at the beginning of the, whatever, start things off. I can do those things separately. I can set up the initial charge and the initial current. And then you want to look for, of course, charge is always real, current is always real. But along the way, you've got these complex functions. They all work together. You do it right so that everything is real, even though you've got all this complex arithmetic going through. Okay? And that relies again on the superposition. Okay, so we're now going to talk about the wave equation. And there are lots of wave equations. So this one is what, if somebody just says the wave equation, they probably mean this one, but there's a whole bunch of them. And the Schrodinger equation is another wave equation, which will be different than this one. And then there are lots of them, because there are lots of different kinds of waves. So water waves on the deep ocean, for example, this will describe something like that. You could have a wave in a piano wire, wire under tension. You could have sound waves, light waves. There are lots of different kinds of waves which are described generically by wave equations. There's a wave equation for light and vacuum, which we'll talk about here in just a second. There's a wave equation for light in glass, which will be different than this. So there are certain generic characteristics of wave equations. We're just going to be looking at one here, so don't get too hung up that there are some things that we'll talk about are generic for all wave equations. And also there's two different categories of wave equations generally. One is linear, in which case the superposition principle applies. So that would be if I have a one light wave, one ray of light coming through and another ray of light coming through. The resulting field can be expressed as a superposition of the individual fields. But there are situations where that doesn't work. But there are situations where the resulting field is not simply a superposition. And so that's called nonlinear. And there are lots of interesting physical systems that are nonlinear in their response. And there are, for example, optical systems. If you get a laser is usually a nice example of an intense source. You can have interactions between two laser beams in a material, not in vacuum. Well, in vacuum, if it's intense enough. But if you just have an ordinary material, you can, if the intensity of the laser is high enough, you can actually get crosstalk between the two laser beams. And that's a nonlinear response of the material. We're not going to be talking about nonlinear materials. We're just going to be talking about everything is linear in what we're doing this semester. Which means that, again, generally mathematically, if I have one solution, I have two solutions that are independent, I can add them together and get another solution. Okay. All right, so the wave equation that I'm going to talk about, down first, is of a general form like this. And I'm going to give you some physical examples that meet this, but the idea of the empiriometric is that mathematically you can consider two different things that mathematically look the same. And so the mathematics that I use for one can probably be transferred over to the other case. And the empiriometric is good about kind of closing in on itself. And then you just talk about generically about a wave, not water wave or sound wave or something, but just wave. And you lose all those distinctions that are real. Water wave is not the same as sound wave. It's not the same kind of thing. So one way to get the wave equation. So let me first, I guess, work you through some symbols. Hopefully everybody, you were with me in the spring, you know about this. This notation here is a partial derivative. I have a function of more than one variable. Could describe a wave height at different times and at different locations. And this is a derivative of this function holding t fixed, taking a second derivative with respect to x. And that's this partial derivative, like this. And this is doing it twice. And this is the same thing, holding x fixed, take the derivative with respect to t. Okay, so those are called partial derivatives. And they're really kind of obvious because it's just what you would do if you just considered the x dependence of this function by itself, or the t dependence. So operationally, when you take the derivative with respect to x, you just treat t as a constant. And the same the other way around. If you take the partial with respect to t, you treat x to be a constant. And so everything falls through. Okay, so this is the generic wave equation. As I said, there are lots of wave equations, but this one is somebody just says the wave equation. They're probably meaning this. This corresponds to, like I said, water waves out on the ocean, not near the shore, but out on the ocean. Sound waves, waves on the string. I'll show you here in just a second how we get to this. And there's a term here, c, which is a generic speed of propagation. So the wave is moving in some fashion. You get something that looks like a wave propagating through. C is the speed of propagation. Material, whatever the substance is that's propagating in. Okay, so you can see how this might work. For example, suppose I have a piano wire. And I'm measuring the deflection of the wire off of the average. That is, there's some kind of unexcited, that is just a stretch without any vibration in the string. And then if I pull the wire off of that zero deflection, there's going to be a restoring force. If I stretch the wire like this, there's going to be a restoring force. It's pulling the wire back to the straight condition. And that depends on the curvature of this function. If I represent this by a height, then and if I look at the little piece here of wire, so this is H. At some time T, I take a snapshot. I consider a little piece of the wire is going to be a restoring force, pulling it back down like this. And so there's a force acting on this, and we would say if the string, the wire has some kind of mass density, then we would say that the force acting on it would be the mass density times the acceleration of that piece will be equal to some kind of modulus, depends on the tension in the wire. And the curvature. H with the second derivative of H with respect to X, right? The double dot is time derivative, primes are X. This is just a Newton's second law applied to just a piece of the wire. You can see it's the curvature and not the slope of the function, because you can see this piece right here is being pulled down because the wire is curved. There's a part here going through the origin where the curvature is 0, coming through an inflection point. There's no force acting on this piece. It's going to stay where it is. And so this is a hand waving, really quick derivation of this wave equation for a string. But there are a lot of things that are going on here that are kind of hidden by this. I'm not really telling you how the parts of the wire move, except that there's kind of a vertical deflection. Remember, I said it looks like water waves. But if I have a wave on the ocean like this, and this is the height of the water, and suppose this wave is moving to the right, the water cannot move simply up and down. It has to move left and right, some. So if you look at a piece of water here, as this wave is, say, propagating this way, the piece of the water is kind of moving through a kind of circular pattern. Let's see, maybe going this way, okay? So if I look at a packet of water down here, part of the water piece, it's moving in a kind of a circular motion, and the deeper you go into the water below the surface, the smaller that circle gets. But there's no net motion of the water this way, or it's very little. For this, at this level of precision, there isn't any. Okay, we represent all of this again by the height of the water, but it says nothing about what the parts are doing. Right, all of that gets kind of thrown away, just disappears somehow. So to derive the wave equation for water, I have to consider actual fluid dynamics to show that I get a wave equation for that. Similar thing happens with air. Sound wave, one kind of sound wave is called longitudinal, which means I get compression and rarefaction. I get more dense air, less dense air, more dense air, less dense air. And this sequence can propagate through it. And that's what happens in air. We have sound in air. And so I talk about the density of the air, and that becomes the deviation of the density from the average. And then I could represent that as a wave equation. Same sort of thing that happens. But I'm kind of lost in this description, the details of the dynamics of the air. Right? It's all been kind of swept under the rug in a way. It just means that you're not focusing on the details of the parts, looking at some general characteristics, like the deflection of the wire from average, or the height of the water, or the pressure of the air, that kind of thing. Okay. All right, so this is just wanting you to have a general understanding about why this is so general. Right? This is like the simple harmonic oscillator of fields. We had the simple harmonic oscillator, and I said the simple harmonic oscillator will show up everywhere in physics. The wave equation will show up everywhere in physics. You'll have lots of different situations where they'll mathematically will look similar. And that means what I'm going to say here generically about wave equations is going to transfer to other wave equations with some, possible caveats. Okay. All right, now, first thing to note, we're going to look at solutions to this equation. We looked at solutions to the simple harmonic oscillator. Use complex variables, and we're going to look at use complex variables to solve this equation as well, the general solutions. But now, the initial condition, how do you specify the initial condition of this? Well, you would have to specify both the initial height of A and its initial velocity as a function of location. So now we have the initial conditions are two functions. The shape of the wave at the beginning and how the parts individually are moving. The impetus that each little part has got initially. So we have two different parts now. So the initial conditions are like this. Same strategy. We're going to look for solutions to the differential equation and then match to initial conditions. General strategy is going to be the same. And again, we're going to have complex functions along the way. And we might think, wait, how could that be? Again, it all works out. The coefficients are matched in such a way, everything will work out. Okay. All right, so we have the superposition principle will hold. I have a solution and another solution that are different from each other, and the sum is another solution. And that will allow me to construct general solutions matching any particular initial conditions. And that's going to be very helpful. Okay, so, all right, so here's an interesting solution. It's going to be a little surprising. I'm going to try a solution of this form. Let's just see what happens. Okay, so now I need to take the two derivatives here in order to substitute it in. So I'm going to guess. This is a guess. And there's only one parameter in this guess, b. What value, is there a value for b such that this will be a solution? And then we'll study this solution. This is a very general solution. Okay, so I take a derivative. I have to take two derivatives. So the derivative of this, now I hold t constant when I take the derivative with respect to x. So this is just the derivative of this b function, whatever it is. I don't know what it is. It's just some function, any function. Second derivative. Okay, so far easy. I need two derivatives in time. What do I get? Take the time derivative of this. X is a constant. I've got a negative b in front, so chain rule. Okay with that? What do I get for the second derivative?
B squared.
Yeah, plus b squared times the second derivative. No. So dot is specific to time derivative, but prime is anything else. It's the derivative of g with respect to its argument.
Okay.
And its argument is x minus bt, but which has also x and t dependence, right? So it would not be g dot. This would be f dot and f double dot. But this was just generally the derivative of g with respect to its argument. Okay, let's substitute it in here. So we have then g double prime. We have minus b squared over c squared times g double prime. And g double prime is a function of x minus dt. So we can factor out the g double prime. X minus bt. All right, now this can be a solution for any G whatsoever. As long as what's in the parentheses out front vanishes. In other words, as long as B is equal to C. And we have another one where B is minus C, but I'm going to talk about what that means here. I'm just going to pick one of them. But this would be a solution, right? Okay, so B here has to be the speed of propagation. So let's go back, and we did something like this before, but I'm going to look at this. Let's set the argument to a fixed value. So I'm going to watch some feature of the wave function. So in other words, if I look at it at f equals at f at time 0, it's just the initial shape. Well, it doesn't even have to be oscillatory. It could be a tsunami, right? G is just the initial shape, whatever it is. It doesn't have to be oscillatory. So this is the initial function. Anything will work here, as long as it does this. So let's pick a value for, let's pick the peak here. And let's suppose that this thing is set up so that, let me do it this way. Let's just suppose it looks like this, just to make it easy. Let's suppose it has a maximum at the origin. At later time, that maximum, what's going to happen to it? It's going to decrease. Yeah, that's true. Where's the maximum going to go? The maximum won't decrease. The value at this point will decrease, but the maximum won't. It's just a slide to the right. So at a later time, f of x at some later time, the maximum is going to be over here at a position dt. Right? Because you x minus bt gives you 0, which is what that corresponds. So this is a right traveling solution. You could call it a wave. I would be fine to call it a wave. It's not oscillatory. It's like a tsunami. It's got a direction to it. Big peak, but nothing outside of this huge peak. It's all moving to sliding over to the right. And how do we get a left traveling wave? Well, we pick the other solution here. We flip the sign of this, that gives us a left traveling. And how do we construct that? Well, the piece that I haven't specified here is the initial velocity. So the initial velocity will determine whether it's a right or a left traveling wave or something more common. Yes, ma'am.
I'm sorry, which one did you say you the sign up to get?
Yeah, if I flip the sign here, if B is positive and I use plus, then it travels to the left.
Okay.
Because x minus bt is equal to 0. It will follow whatever feature is at the origin initially. So I said x plus bt is equal to 0, then I've got something that's going to the left. That makes sense? So B here is the speed of propagation or the velocity of propagation. Either if B is positive here, it means it travels to the right. If B is negative, if we just flip the sign of this, then it's going to travel to the left. Is there a question? It's kind of interesting. So the wave equation here is just very general solutions. Lots of possible waves. Which one do you use? It depends on how the thing is set up. It depends on what makes the wave to begin with. That's what we haven't specified yet. Propagation is just going to take what's there at the beginning and move it, propagate it. And so that's why we get these very general looking solutions. One thing I didn't mention, you get an equation like this from electricity and magnetism. If I take Maxwell's equations and I solve them away from the source, right? An electric field is generated by a charge, plotted. If that charge is moving, then the electric field is going to be propagating through and it's going to be changing at time. And it's also not going to be uniform. It's going to be different in one place than another. I get a wave equation for the fields where this c is the speed of light. So I get the wave equation is again a product of Maxwell's equation. And then you can talk about radiation, how things, electromagnetic waves propagate through the planet. Okay. Yes.
Dr. Dahl, why is it that it must maintain its shape?
Yeah, it does. Yeah, and that's just a characteristic of this kind of physical system. That's going to maintain its shape. If I have an antenna, let's talk about electromagnetic waves, for example. If I have an antenna that's oscillating current and generate an A field, you could think of it as a B field or a D field, but it's better to think of it as an A field, an oscillating A field. And the A field is just going to, remember, the A field goes in the direction of the current generates. So this oscillation gets propagated through. Whatever the antenna did in the past is fine. You'll find it out here somewhere, right? If it did it, you're thinking about what did the antenna do 5 minutes ago? Well, if I go far enough out here, 5 light minutes out here, I can tell you what the antenna was doing. The planet is just propagating what the antenna gives it. And that's why it maintains its shape. So this propagation, whether we're talking about water waves, where again I have some kind of source, I'm doing something, that's propagated outward by the medium. So it's just doing what the source told it to do. And then it's just propagating that out. So the shape here is just a kind of representation of history. If this thing is propagating to the right, where did it come from? Where's the source? Over to the left, someplace. Don't know any more about it than that from just this. If in the past, it was over to the left somewhere. And now whatever happened in the past is coming through. You're seeing. That's why it maintains its shape. The medium in this case is just has perfect fidelity to the source. The source does its thing. The medium is just responding in a very passive way and just does what the source did. And so this propagation, one part of the planet passing it along to the next, is just recording in a way, just responding in a way to what happened over here earlier. And that's what propagation is. Does that make sense? Very general, right? Okay. All right, so now let's consider an oscillatory solution. This was not oscillatory, right? It's a pulse or a packet. So a pulse or a packet. By these things, I mean something that's kind of confined, it's isolated. It might be the antenna is switched on and off real fast. And then I get an electromagnetic wave propagating outward at the speed of light, and it's a pulse. So if I do this pulse, it's going to take some time for that pulse to reach across to the next building over here. It's not going to be long because we're talking about light. But it takes time, finite time. And it just, over there's just a pulse. Shows up after time goes. So now let's consider an oscillatory solution. A solution like this. Again, now we have 2 parameters. And remember the 2 parameters? We talked about them last time. This is related in the frequency. This is the frequency is you normally talk about the frequency. This is the spatial frequency, the wave number. So if I graph this at some fixed time, I'll have an oscillatory solution, and the distance between crests is related to the wave number. This is if I take a snapshot at some time. Or if I take some position and look at the oscillation in time. So this is versus X for a snapshot. If I take some position at particular x, then I also get an oscillatory behavior. The distance between maxima period and the frequency, angular frequency, is related to the period. Remember? Now we're going to try a solution like this. And it won't be surprising to you to find that this is a solution, because what I wrote before was actually, this is a special case of what I wrote before. But we're going to try to just work it out, the special case, see how it works. But this is oscillatory. This is explicitly oscillatory. And this is what some people mean by a wave. We have this kind of oscillation that goes on. But really, this pulse or a packet is really a wave. It's just localized. So I just want you to recognize that wave equations admit solutions which are not obviously oscillatory. Right? Wave equation can be whatever the source tells it to do. Well, if the source is oscillating for a long time, then this oscillatory wave is going to be propagating outward and just keep doing it. And so over here somewhere, after the source has been operating for a while, it'll look like this. Right? So where's the source? Or that way. Again, how do we know which way this is moving? We set this to 0. Pick a feature, which would be a maximum. Set this equal to 0, and we get kx equals omega t. So x is some number times t, which is positive number times t, so it's sliding to the right. So this is a right traveling wave. This is an oscillatory wave, not just a pulse or pattern. Okay, let's go through the same exercise. We need 2 derivatives in x, we need 2 derivatives in t. When we do a derivative in x, we get a k and a negative sign because it's cosine. And then we take the next one, we get from sine to cosine without a negative sign. So when we take 2 time derivatives, 2x derivatives, minus k squared a cosine x minus omega t. Right? First one gives a negative sign because it starts as a cosine. Next one goes from sine back to cosine without a negative sign. We get a net negative sign. When we do the second derivative with respect to time, what do we get?
Essentially the same thing, but with
Yeah, what's the sign out front? We get an omega squared. And it comes back to cosine because it takes 2 derivatives. You could write it like this if you want. Instead of k squared, it's now negative omega squared. But what is the negative? What is the square of negative omega? Positive omega. So this is negative omega squared a times the cosine. Okay, we substitute this into the wave equation. Just looking at solutions to the wave equation. We haven't matched the initial condition. We're just looking at the solution to the wave equation, the general solution. So we substitute this in here. And once again, this is the same common factor in both. So we can write this as negative k squared plus omega squared over c squared times a cosine. Okay, it'll be a solution if what's in the parentheses out front vanishes. So there's a particular relationship between the frequency and the wave number. If the frequency and the wave number are positive in the solution, then they have to be, this is a correct relationship between them, right? So I've chosen here that k and omega are positive numbers. And then this one has the solution where the omega is equal to k times c. That's called a dispersion relation. What does it mean? All right, you've probably seen this in a different form. Remember, k is related to the wavelength, pi over the wavelength. So this would be omega times lambda is equal to 2 pi c. Or if you use not the angular frequency, but just the frequency, that is with a factor 2 pi, then nu times lambda is equal to c. Seen that one before when you were studying waves and light waves. There's this relationship, actually any waves, have this relationship between the frequency and the wavelength. But what's going on physically? Remember, this comes from some source. This thing is moving to the right. The source is over here. I don't know what it is. But I do know one thing about the source, that it's over here, but I know something else. What is that?
That is source. I'm sorry, what was
It's a question. All right, don't answer until you know the question. I know the source is to the left, because this is a right traveling wave, but I know something else about the source. Any idea? Anybody got it? About it for a moment. Picture this wave oscillating, moving to the right. The source is over here. If I'm just a little bug or a receiving antenna, there's a frequency. What sets the frequency?
source?
The source. Omega comes from the source. This is set by the transmitting antenna or by the source. This is oscillating because the source is oscillating. The wave packet was not an oscillating source, it was a pulse source. Okay, so this is the kind of solution you get from an AC antenna. An oscillating antenna is just oscillating at some frequency. And then over there somewhere, after the antenna has been operating long enough for the signal to get to this place. And now the plana, the field in the plana, or the water wave, whatever it is you're talking about, is oscillating at the frequency that the source had sometime in the past, right? The source might be off now. But what it was doing in the past is out there somewhere. Okay, so now the source does not set the wave number. The source doesn't set the wavelength. What sets the wavelength? So the frequency is set by the source. The wavelength is set by the medium through the speed. Right? Lambda here is going to be 2 pi. Well, it's just this, right? 2 pi. Lambda is 2 pi over c omega. So lambda is determined by the speed of propagation in the medium and the frequency of the source. Right? You can see how this works. The source is doing this. The wave is propagating outward from the source. So this distance that the thing travels is determined by the speed. So the maximum distance from maximum to maximum is determined by how long it takes for the source to come back to its max and how far it's traveled in the meantime, the wavelength. See how that works? Very important point.
So it's set by the speed of the propagation of the medium.
Yeah, that's right. And the frequency of the source.
And the frequency of the source.
So this is set by the frequency of the source and c of the medium, whatever it is. The speed of propagation in the medium. If this is light, it's the speed of light. So you're going to do a few exercises with this for homework for Monday. You're going to superimpose solutions, see if, there's a left traveling wave. What if I use sine here, S-I-N? Is that a solution? What if I have a, and you'll find out it is, how about a complex exponential? How about e to the I kx minus omega t? That's also a solution. It's complex. You talk about superposition. Can I take a right traveling wave and a left traveling wave and get a solution by summing, adding them together? Yes. What about a product? Can I take the product of a right traveling wave and the product of a left traveling wave? Will that be a solution? I'm not going to answer it. You got to work it out. Superposition we've talked about is add them, or product work, multiply solutions. Okay, so this is for your investigation for Monday. On Monday, I'll talk about this and the solution, and then we'll answer more questions about the test. There's a practice test on Canvas. We have a test in class on Wednesday, so you'll no homework due Wednesday. Study the practice test. I want to look at it before Monday, so if you have any other questions about, not sure how to do something on the practice test, you can ask them in class on Monday, rather than trying to on Tuesday. Wednesday morning. All right. See you later.